I looked at this, what's the unit of r? If r is the radius here, just some length unit, meters usually if we're using SI units. So this would be VT would be the units of meters. What would the unit of omega be?
Would be seconds.
Radians per second. Okay. That gives you units here of meters times a radian per second for your answer for V. But when you write your answer for V, this just drops off. Okay. Because we don't need to carry that radian around everywhere, we could actually write the unit for omega as 1 over seconds. And it's written that way sometimes, because the radian is sometimes just left off. We keep it here, kind of like that placeholder to remind us that we're talking about a rotational and angular velocity here with the omegas. But whenever you go back and forth here, you're going to have to know when to keep the radians or not. And in a case like this, you don't ever write your V in units of meters times radians per second. Switching back and forth between this right here, you always leave one of them off. And you'll see here that if I went back the other way, and if I said omega here was V over R, the radian won't be in there, because you're going to have a meter per second divided by, you know, if you look at it like this, omega is VT over R, and solved it that way, you'd see units of meters per second here divided by a meter there, and you would have units of 1 over seconds. You're not going to see that radian in there when going back and forth between the V's and the omegas, or any linear to angular quantity. So you're going to have to get comfortable with that, just knowing when to keep them. This is one time where you just need to know what units you're supposed to get and not trust what you have written here. And you can only really do this with the radian. Okay? I mean, it works out this way here, whether it gets left on or not. And that's why you'll see these sometimes written out as just units of 1 over seconds or seconds of -1 for the omega. We keep this here now in this class just to remind us that this is an angular velocity. Radian should remind you of that. Okay, so your V is omega r. This T, sometimes we will leave off. There isn't going to be a difference between the tangential velocity and the regular linear velocity. They are the same thing. Later on, when we talk about acceleration, though, we're going to have to make sure we keep it. Okay. I'll show you some more about that later on, where you'll kind of see where that little t for tangential will be left off and why you should know that it's okay to leave it off. Okay. But for now, I'll leave it like that. While we're here with that picture, let me just kind of go back a second and then tell you, or write down at least, the sign conventions. For rotations. A counterclockwise rotation is positive. And clockwise is negative. That is based on that right-hand rule that I mentioned, but we don't have to use that. That's where we get those signs from. That's how we know positive or negative. We won't use this a whole lot with our kinematics, because most times when we were moving before, if I told you we were driving a car and I didn't say which way we were going, we almost always chose to just move to the right, because that was easier, that was positive. With rotation, we're always going to just assume that we're rotating in the positive direction, so we're not going to have to really think about whether that's clockwise or counterclockwise right now, because the signs won't matter that much. Since we're going to be able to start at 0, we're going to be able to just choose our direction of rotation. If I say something's rotating, it doesn't matter which way it's going. Okay, if it's going at some speed, then we're just going to choose that to be rotating in that positive counterclockwise direction. But these signs and the idea of counterclockwise being positive and clockwise being negative, we will use that extensively when we get to torques and we talk about the forces that make things want to rotate. If a force makes something want to rotate in the counterclockwise direction, so if I push on this up, That's a positive force that we used to know about, but now it's just talking about what direction does it make want to rotate. Now if I look over on this side, if I fix this over here with my right hand, and I push up over here, this is wanting to rotate in which direction? Clockwise. So here I have an upward force that you might want to say is positive, but I'm rotating in the counterclockwise direction. That's the part that we're going to think about when we get to forces and torques. So we do want to be using those signs. We just won't need them a whole lot right now. Maybe just a little bit. Once we get to all of our equations with all this stuff, we really won't use it that much. So there's our V. Let me put another circle up here. And come back to some delta theta on here. This V here is a measure of your linear displacement per time. Right? How fast you're going around the circle. Not how many radians you're making per second, but how many meters you're making per second. So how far around do you go with respect to time. That V is related to not this angle here, but to the distance that you're traveling here. Okay? This distance we call the arc length. And the arc length we use an S for. And this is just equal to R theta. This could be R, or maybe should be R times delta theta, but your theta is always going to be your angular displacement. So in this form here, S is equal to the arc length in meters, theta is equal to the angular displacement. This has to be in radians. This equation here does not work unless your angle is measured in radians. And then R is the radius. And that can be in any unit. But the SI unit would be the meter if we're going to get an arc length in meters. Okay. You'll notice again right here in this equation, if I were to plug numbers in now, and I said I had an angular displacement of, let's say, pi radians, and my R was 1 meter, I'd have 1 meter times something in radians, and you would think that you would have units there that would be a meter times a radian. Okay, here's another case, though, where you're getting an arc length in meters for that distance up here. You're not ever going to write that out as a length in units of meters times radians. There's a case where you're writing a linear quantity, something in meters, the radian that you have right here just drops off. Okay? You don't keep that as a unit. So for many of you who don't check your units anyway and you just write down what you think the answer should be, that's not going to be much of an issue. But for those of you who are actually looking at your equations carefully and saying, my answer is whatever I have right in here, you can't do that with your radian measures. Okay? So just know that when you're doing those. Everybody else, most of you who don't look at that, you'll just say arc length should be in meters, your R is in meters, you'll write your answer in meters and hopefully be okay with that.
Radius.
Okay, so we did velocity or speeds here already. The next thing I'm going to talk about is one more way we need to define some things, so speed, and talk about time now for rotations. Then we'll get to acceleration. So time required to make one complete revolution. It's called the period. very clear with your notation now because t is not the same thing as little t. Okay? This t means sometime in general. Capital T means the period. This is just the time it takes to make one complete revolution. So what would the period be of the second hand on the clock?
60 seconds.
60 seconds? Took you all a second to think about that, but yes, we all know that. There's a question, one of the first questions on your homework has something about if you're going around for however many minutes, 30-something minutes, it wants to know how far does the second hand, the minute hand, or the hour hand in your clock travel in some amount of time, 30 minutes, 35 minutes, whatever it might be. So you'll have to use your ideas. Well, of course, you know how far things go around or how long it takes things to move around in one complete revolution. And then just, you're going to be using an arc length to figure out how far they go around. But some people just sit there for a while and just not really think about how long it takes the hour hand to go around in one revolution. What would the period of the hour hand on your clock be?
60 minutes times 60 seconds.
The hour hand. The minute hand goes around one revolution in 60 minutes, right? What is the period of the hour hand on your clock? Look at the clock.
12 hours.
Yeah. But that's what I'm saying. Just if you need to, stare at the clock and look at it, because some people will just sit there and not be sure what to do with that problem because you're not really thinking about the clock, or you don't use clocks like that and you just look at your phone, so you're not used to looking at a clock anymore. But you might need to stare at a clock on the wall and think about how long would it take that to go around once. That's the period. And the question's not asking you for the period, but knowing how long it takes to go around once would allow you to figure out how far it goes or how long it takes to go around in whatever minutes you have in that problem. Okay. So
that's not measured in seconds. Like time is always in seconds. That's just whatever it is.
Time period could be in any unit. The SI unit for period would be time, but physically, as just talking about how long it takes to make one revolution, I could use any time unit to describe that.
Okay.
If I'm going to use that in equations that are all based on SI units, then yes. So the period has regular units of time, just like anything else. But I could say 1 hour, 60 seconds, 60 minutes as my period, and then I just need to know when to convert that. So you could really say that could be anything you want it to be, any time unit. How you use that in something else then would determine what units you really want to use in your problem. The frequency is the number of revolutions per second. So in keeping with this SI unit of the second here, then the frequency is defined based on that second, and it's the number of revolutions per second. Okay. So frequency little f is just 1 over the period, 1 over capital T there. This has units of 1 over seconds, which is the same thing as a second to the -1.